Welcome to everyone. Welcome to this webinar. We are here to see the presentation of Óscar Nieto Cerezo for this webinar of June. He will do the SYMBIOPTIMIZE platform presentation. As always, this webinar is being recorded, so they will be presented to you in our YouTube channel, but also for everyone, the slide will be also sent by email. Just to mention, this webinar will be the last one before the summer break of July and August, and we will be back in September with new ideas and with new webinar. As always, he will do the presentation, and after that you have the Q&A question box, so you could put whatever you wanted to mention to him according to his presentation or the doubt that you could have. So before giving Óscar the floor, I would like to make a short introduction of himself. He is PhD in engineering from the University of Liverpool. He has also previously completed his master degree in renewable energies. And also he has a bachelor degree in environmental sciences. He's now currently lecturer and researcher in the Circular Economy and Industrial Sustainability Research Group at the Mondagron University in the Basque Country in Spain. His work focuses on the modeling and simulation of business in the context of renewable energies and the energy transition. He has worked as economic modeling manager, also in the University Polytechnic of Madrid, and he has developed several economic models to support the investment of the city in terms of climate neutrality. Also, he has been working in United Kingdom, and he has also taken part in the UK Climate Change Act. So from the moment, I'm going to stop sharing my screen, and Óscar, the floor is yours.
Fantastic. Thank you very much, Almudena. Well, this I'm very much happy to share some of the work we are doing here in the Circular Economy Research Group. So the purpose for me of this webinar is to share this preliminary work. It's a platform that we have been developing in the last few months. And I'm very much convinced that some of you are already working on this research path. You are also developing your own tools. You are always developing your own platform. So I was thinking that at this point, it was a great opportunity to share this piece of work at this early stage, mainly to look for collaborative partnership, to find some synergies we might find between different universities, and probably to develop this further, and also to build a consortium for a project, to write a proposal for an Horizon project or something like that. So I think I will start with first. The plan today will be to start developing, presenting the framework, so the methodological logic behind the platform, and then we are gonna go to do some demonstration of the application itself, right? So, as I said, this I briefly introduced the methodological logic behind the application, including the motivation, implementation gap indicator, modeling framework, and how this translates into an interactive application. Then I will show how this logic had been translated into a SYMBIOPTIMIZE platform. And then we will present, we will give a step-by-step instruction on how configure firms, supply and demand matrices, synergy definitions, and then we go to the mixed integral linear programming optimization. And finally, we are going to see how these results are displayed. So SYMBIOPTIMIZE is not just a standalone digital tool. It's based on an academic paper entitled Measuring the Implementation Gap in Industrial Symbiosis Recovery Under Uncertainty. And the key idea is that the paper provides the analytical foundation, while the application makes the foundation operational through an interactive decision support workflow. Okay, so The manuscript is currently available in Social Science Research Network and is under review in the International Journal of Production Economics. This is important because the platform is grounded in a research framework developed to analyze industrial symbiosis recovery under uncertainty. So the paper asks how we can distinguish between what is technically feasible in industrial symbiosis network and what is actually realized when firms face cost, uncertainty, and implementation barrier. So before entering the app, I first summarized the research problem and the modeling framework that is the core, as I said, of the application. So the motivation of the paper is that many industrial symbiosis opportunities are technically feasible, but they are not always implemented in practice. In principle, the waste generated by one firm can become the primary input of another, as we know, and this can reduce waste, substitute virgin materials, and improve resource efficiency. However, in practice, these opportunities often remain underutilized or fail to persist over time, right? So the reason is that industrial symbiosis is not only a technical matching problem, it's even in an extent, even if the exchange is possible, it might still face structural limits or implementation barriers. So we understand for structural limits to problems such as limited residual supply, limited substitution potential, or material compatibility constraint. And by implementation barriers, we refer to problems such as activation costs, coordination requirement, processing costs, uncertainty yields, and fluctuating prices, right? So this distinction is very important because each problem, the nature of the problem requires different response. So this leads to the main research gap addressed in the paper. The research gap is that existing approaches often analyze technical feasibility, optimal deployment, or uncertainty independently. But in industrial symbiosis, these dimensions are normally connected. If circularity is low, so the industrial symbiosis is not implemented, we need to understand why. Is it because the system doesn't have enough structural recovery potential? Or is it because technical feasible opportunities are not being implemented due to cost, coordination problems, or uncertainty? This distinction matters because the same low circularity results can imply very different interventions. If the problem, for example, if the problem is structural, we need to redesign the system to introduce new technologies. If the problem is implementation related, then the priority might be reducing activation costs, improving coordination, lowering recovery costs, or sharing risk between firms. So the research question is, how can we measure the gap between a structural feasible circular recovery and realized recovery performance under uncertainty? So to answer these questions, the paper developed a scenario modeling framework that measures the gap between structural circularity potential and realized recovery performance under uncertainty. The paper makes three main contributions. Defines a technology-based structural circularity benchmark. This benchmark represents what could be achieved if we only consider technological feasibility and structural recovery potential. Second, and most important, it integrates three modeling layers: enterprise input and output accounting, mixed integral linear programming optimization, and Monte Carlo simulation. And finally, it quantifies an implementation gap. This gap helps identify low circularity and help identify whether low circularity is mainly due to structural limits or implementation barriers. This is useful because it turns the model into a diagnostic tool. It doesn't only say whether circularity is high or low. It helps explain why a circularity is low, for instance. So this slide shows the implementation gap indicator. The idea is simple. We compare realized reduced disposal with a structural residual disposal. structural residual disposal represent the amount of residual or waste that cannot be recovered because of structural and technological limits. And realized residual disposal represent what actually remains unrecovered after considering cost, activation decisions, recovery constraints, and uncertainty. The difference between them is the implementation gap. If the gap is large, then the system has recovery potential, but this potential is not being realized in practice. This highlights that implementation barriers such as cost, coordination, processing requirements, or uncertainties are the main reason for this lack of implementation. So the implementation gap might help distinguish between the different kind of problem, no? For example, the lack of structural potential or failure to implement feasible potential. Why is the implementation gap relevant to the application? Because the analytical tools used in the application framework are justified by the construction of these indicators. So here, to calculate this implementation gap, the paper combined 3 modeling layers. As we said, the enterprise input and output accounting, which is on the left-hand side in green, the mill optimization, mixed integral linear programming optimization, and Monte Carlo simulation that is on the right-hand side. So the first layer is the enterprise input and output, and this layer represents the physical structure of the industrial system. In simple terms, it describes how different production processes are connected, what inputs they require, and what waste they generate. So this layer is important because it gives the model its physical foundation. It defines the input demands of the system, the available waste, and the material balance relationship. So it helps to quantify this relationship in physical terms. So this means that this layer answers questions such as how much input is needed, how much waste is generated, and what are the physical limits of recovery. This is essential because recovery cannot exceed what is physically available, and substitution cannot exceed what is actually demanded. So before thinking about cost or optimization, this layer defines the constraints of the optimization problems. In other words, the optimal solution must fall into the structural opportunity space provided by this layer, right? So the layer in the middle, this is the layer that transforms the physical opportunity space into a decision problem. So the optimization model decides which recovery pathways should be activated and how much residual resource should be exchanged. It uses 2 main types of decision variables. The first one is the flow variable, which represents the quantity of resource exchange, the quantity of waste exchange between the firms. For example, how many tons of plastic scrap are recovered and used as a secondary polymer input. The second is the activation variable, which indicates whether a pathway is activated or not. This is important because an industrial symbiosis exchange is not just a physical flow. It might require coordination, contracts, logistics, infrastructure, processing capacity, and so on. So this optimization layer also considers economic and technical constraints, and it considers virgin input costs, disposal costs, recovery, activation costs, and many other relevant costs, right? So therefore, the optimization layer doesn't simply maximize the use of waste. It decides which exchange are economically viable or reasonable, given the physical and operational constraints of the system coming from the input and output method. So the final layer, here on the right-hand side, introduces uncertainty in the analysis. So in a real industrial system, supply of waste and demand of primary input are normally not fixed. So the waste available might change, production levels might fluctuate, and recovery yields might change. And of course, virgin input prices might increase or decrease. So for this reason, the model doesn't solve the optimization only once. And this is important. Instead, Monte Carlo simulation generates many possible scenarios, and each scenario represents one possible state of the industrial network under uncertainty. For each scenario, the model updates the uncertain values and then solves the optimization problem again. This produces a distributional result rather than a single deterministic answer, as we can see here on the bottom. So this is important because it allows to evaluate the robustness of the decision making, right? So we can see whether a recovery path is activated in many scenarios or only in a few. And we can also analyze how cost, emission, circularity, and resource recovery vary or changes under different operating conditions. In other words, the Monte Carlo layer informs how stable or uncertain the recovery decisions are. So, okay, together, all these three methods together create the logic of the paper and also the mechanism behind of the application. So at this point, well, let me just also mention that the platform used this modeling logic and turned into a practical tool with an interactive interface. So therefore, given this, the main contribution of the platform is to put the research framework into practice, because it helps users move from possible industrial symbiosis ideas to a clear list of partnership. It will come up with a clear list of what is feasible, what is economically feasible, and what is not possible in terms of physical terms and monetary terms. So, so at this point, I would like to switch to the platform and to do a little demo to introducing some data and to analyze the result. What is the potential of the Symbiosis platform, and what are the main steps forward, and where we are heading in the next few months, okay? So. I don't know if everybody can see the, yeah.
Yes, Oscar, we are seeing the screen.
Okay, that's great. You can see that. Okay, that's great. Perfect. So, right. So the application, well, this is the front cover. We are gonna go straight to the platform, and I'm gonna explain the main feature. So let me check here. So the application is organized into four main etaps. No? We got firm management, data matrices, optimization, network visualization, and one additional, that is the user guide, where is all the documentation. So for this, the first tab is the firm management, and is where the user defines the firms included in the network. For each firm, the user can specify the type, the geographical location, the quantity and type of waste generated, and the primary input required, right? So this for the first firm, so as we know, this is the starting point before we're running, and we've got a very interesting point here, which I think this is one of the highlights of the platform, and is that the first decision we need to do as a user is the data move. The application allows two possibilities: to use real data or to use an estimate, because normally it's extremely difficult nowadays to get data directly from the firm. So we can use the enterprise input and output method to estimate the quantity and the type of waste and the quantity and type of primary input we need. So this in the real data mode, we can I'm gonna click it because we are gonna use that, and we are gonna use some company names. Let's say Fagor, which is a typical firm from the Basque Country. But I would like to say that this real data, of course, it can come from electricity bills, water, production record, invoices, and probably, as I said, at the early stage, it's very difficult to obtain this data from the firm until you don't build some trust and so on. So, however, we've got also, if we don't click that option, we've got, we estimate the data. And in that case, the user doesn't need to enter all real supply and demand values manually. Instead, the application estimates these values using 3 elements: the type of firm, the activity level, and technical coefficient. So the application use all these pieces of data, pieces of information to create and some estimate values of what is the level of production of the firm, what is the supply of waste, and what is the primary input that they need to carry out their activities. So all the formulation behind this, how these values are estimated, are in the paper. I will not go details of how this is calculated, but now in future version, by selecting the type of industry we are, the number of employees, and the size of the plant, we can just calculate an estimate of the supply of waste and the primary input. So, given this, I would just provide details for the first firm. We are going to have 5 firms, but the first one, it will be Fagor from the industry type manufacturing. And I'm going to use 50 megawatts for waste heat. The plastic scrap, it will be 5 tons. This is only illustrative value, of course. And this 30 cubic metric of wastewater. And for the electricity, we are going to use 90 megawatts. That is the primary input I need to carry out their activities, 30 cubic meter of water, and 20 tons of polymers. This is, no, well, this, we're going to leave it for this one too. Okay, and sorry, we're going to put 40 here, just to have some better representation. And then, okay, so we do the same with the other companies. We in this version, we can only select 5. So the second one will be, let's call it Mondagron University. And we leave the geographical location by default. All these, they are located in the north of Spain. And we use, it provides 0 waste heat, 0 tons of plastic scrap, and this is 5 cubic meters of wastewater. And for the primary input, 60 megawatts per hour of electricity, 30 of water, and 20 tons of polymer. That is what required. We go to the second one, to the third one, and again, we introduce the values 8 megawatts for the waste of electricity, waste heat generated, 20 tons of plastic scrap, 10 cubic meters of water, and 35, say, of electricity, 20 the water, and 0 tons. And finally, we go perform. Again, we select the real data, and we provide, again, the supply, 6 megawatts, 15 tons, 8, 30, 0, and 18. finally, the last one. Again, use real data. 3. Okay. 0, 5, 40 for the demand, 25, and 50. Well, but that now we have all the data we need. We've got 5 firms. All these firms use apparent in this particular example real data, and here we've got a summary. So once the data is introduced, the application generates a summary table that consolidates the information entered for each firm, right? So at the end of this step, the application contains 5 structured firm profiles, and each profile includes the name, the data entry, the firm location, the type and quantity of waste, the primary input required. The table provides the basic firm information that we need for the next steps. Okay, so the next point is we go to the data matrices. Again, after modeling, after configuring the 5 firms in the firm management, we move to the supply demand. And the purpose of this tab is to organize all the information introduced for the firms into structured tables. Because, as we can see here, right? The application aggregates the information and shows 3 main elements: the supply metrics, the demand metrics, and the feasible synergies here, right? This is a summary of the information we introduced. And here, an expertise will say, well, we can use perhaps waste heat to replace electricity, and the most common synergy path that we can identify here for only the 3 primary inputs, electricity, water, and polymer, considering this application, will be plastic replacing polymer, right? So these are the ones, the synergies we selected: waste heat replace electricity, and plastic scrap can replace polymer. So now there's one of the most important is that this conversion, how much one waste can replace a primary input, is determined by some specific conversion parameters. For example, we got the conversion, the recovery rate that is given by gamma, and is mainly an engineering parameter that stipulates what is physically available, what is physically capable to recover, what is the conversion efficiency of that process to convert plastic scrap into polymer, or waste heat into electricity. For this particular model, for this particular example, we are going to set a recovery rate of 9.9, and for the scrap and polymer pathway, 0.8. The same we could do with the other parameter, that is the maximum substitution rate. That this is more related to political technical limitations, political regulatory policies, and so on. So we cannot replace the full primary input by the waste generated by the firm, because at least, for example, in wind turbine blade, probably we need at least 30% of the product to be produced with virgin material. So in this particular case, the maximum is 0.8 for the heat and electricity, and 0.8 for the plastic scrap. So here we got this is then we can see the balance analysis result, and for the electricity balance, the application shows that 60.3 megawatts per hour are used, covering 24% of the electricity demand. This means that the available heat can contribute to part of the energy demand, but is not enough to cover the full demand, because the other 76% has to be replaced with virgin material. This result is useful because it shows that the energy pathway has a potential but doesn't eliminate the need for conventional electricity. No? So on the other hand, we got the polymer balance, and it shows that given the limitation, the constraints and the technical limitations, we can use 32 tons, which represent 36% of the demand, and the remaining 60% has to be replaced with virgin materials. So here we also have some visual illustration, but only just to complement and for reports if they are needed. So the third label, the third tag, is the optimization, and this is probably the most interesting tab, right? So now there are two steps here. So the first step is to generate scenarios. The application creates different supply and demand pairs, which can, we call it scenarios. This means the application doesn't assume that supply and demand are fixed or perfectly known, and instead it creates multiple possible versions of the same industrial network. This is important because the waste generated and the input demand are uncertain. The second step is to optimize each scenario. For each supply and demand scenario, the application solves the mixed integral linear programming optimization problem, and the objective is to find the optimal resource exchange and the optimal activated partnership for the specific scenario. So the first parameter, we need to configure before that some parameters, and the first parameter is the number of scenarios. We have 100 scenarios here. We can choose 1,000 if we want, and we can introduce the level of uncertainty we want. We are gonna increase the level of uncertainty to 31%. This is how much the baseline values, the ones we calculated in the previous tab, can vary. So, and the third parameter is the distribution. We go in this version, we have only two types of distribution, uniform and normal. We will introduce exponential and wave burst and many other distribution. And also one important extension will be to be able to assign a specific contribution, a specific distribution to each specific synergy pathway. Now they are all, the one we select for is for all. So, okay. Before running also the optimization problem, we need to define the cost of the objective function of the optimization problem. So in this case, the ways, again, all these formulas, the formulas for this particular cost are provided in the paper. So if somebody wants more information, they can dive into the framework section of the paper. So for the heat, for the heat disposal, we are gonna reduce it to 1, and we leave it here for the scrap disposal. For the virgin material, probably we are, let's say 75. We leave it virgin polymer like that. For recovery cost, we are gonna put perhaps 2 as it is. We leave it like that. If for the activation, 500 euros and 800 euros for the plastic scrap connection. And for the transfer, probably we just leave it like that as well. So now we are in the position to run the optimization problem. And then we'll run the optimization problem, and the application then solve the mill optimization problem for each Monte Carlo scenario. The first result shows shown by the application are the summary indicators. These indicators give a quick overview. These are the indicators. It gives a quick overview of the average behavior of the network across all scenarios, right? So the first indicator here on the left-hand side is the average total cost, which is around 80,000. euros. This represents the average system cost after optimization, considering all the costs, the virgin, disposal costs, and so on. And here we've got the sigma, right? So sigma is the standard deviation, and this means that the total cost varies across scenarios. Some scenarios are cheaper, while others are more expensive, depending on how the supply and demand change under uncertainty, right? The second indicator is the plastic, the waste heat used. In this example, we got 56 megawatts per hour, and the standard deviation is quite low. We could say that is selecting some of the waste heat, but not all of it. No, we don't use all the waste heat available. And for the plastic scrap, we got around 40 tons with a quite decent sigma, so it shows some robustness in the result, right? So the active partnerships. In this example, the average partnership is 5.2 with a standard deviation of 0.8. This means that across the scenarios, the model usually activates around 5 or 6 exchanges between firms. These 4 indicators provide the interpretation of the optimization result, and the average total cost tells us the economic performance of the network. So, okay, the results are also broken into 5 main tabs, and we have here the scenarios, the optimal solution, statistical analysis, network topology, and the complete data. So this is only a quick overview, but then we are going to dive into the result of the optimization problem. So for the scenarios, we can say here the app creates each scenario by starting from the baseline supply and demand values and then changing randomly. In this case, values can change. We can see here, the values can change about plus minus 31%. And the table shows the 100 supply and demand scenarios generated by the Monte Carlo simulation. Each row around here represents one possible future scenario of the industrial network under uncertainty. For example, it can be understood that a scenario is a vector of 20 elements that correspond to 10 supply values and 10 demand values. So the table uses also a clear column nomenclature where S represents the supply, F1 represents F1, and for example, each heat represents the type of waste. And then we can also check down here that for D, which is the demand of primary input, F4, it is the fourth firm we have defined, and electricity is the type of primary input we are using here. So the application also provides a scenario variation summary. This summary shows the average heat and supply, average scrap supply, and average electricity, average polymer demand across all the generated scenarios. These statistics here at the bottom provide these are mainly the statistics and the distribution of the generated scenarios, right? For example, the mean shows that the average supply or demand, the standard deviation shows the deviation, how much it varies, these scenarios, and the minimum and maximum shows the range explored by Monte Carlo simulation, okay? So the second tab is the optimal solution analysis, and here is where we want to come because we define in more detail the optimization problem. So the optimization problem has 2 decision variables, right? So the first decision variable is Q, that represents the quantity exchange. It tells us how much resource flows from one firm to another through synergy pathway. For example, Q can represent how much waste heat from Fagor, the company, is used to satisfy the electricity demand of Mondagron University. The second decision variable is Z, and it takes the value 1 if an exchange is activated and 0 if it is not activated. So it provides the partnership between the different firms in the industrial cluster, right? So this means that the model does not decide only the quantities, also decide whether the partnership between firms should exist, right? So this is why the problem, we call it here mixed integral linear programming. We call continuous variables and discrete variables. Also, the objective function is the total cost, system cost, and compromises 5 different costs. The first component is the cost of buying virgin material from outside the symbiosis network. The second cost is the cost of disposing of unused residual resources. The third cost is the cost of recovering this waste, and these include operational costs of converting waste into useful input. For example, plastic scrap cannot be directly replaced virgin polymer without some recovering process. It might need sorting, cleaning, reprocessing, or quality control. So that is the kind of cost it captures this parameter. So the 4 components is the activation cost, let's say an industrial symbiosis exchange might require contract, infrastructure, monitoring system, coordination mechanism, or technical adaptation. And finally, we got the cost of transportation that obviously depends on the quantity exchange and the distance between the firm. So the 2 first costs, in general, we can say the higher the cost of virgin input and waste disposal, the more attractive industrial symbiosis becomes. And the other, on the contrary, if the cost of the last 3 parameters is high, was that it will be more appealing to buy virgin materials, right? So the model also is important to mention that it has some constraints, and these constraints are the ones from the input and output method. And the first constraint is the supply constraint. A firm cannot send more residual waste that is available. The demand constraint, a receiving firm cannot receive more primary input that it needs. And the third constraint is the technical feasibility constraint. Obviously, one active synergy can be used. So in this case, the model can use heat to electricity or scrap to polymer pathways, but it cannot create any other pathways that the optimization problem might find viable. Only the one we select, right? So, and one important constraint is also that if an exchange is not activated, then the quantity exchange must be 0. So in simple terms, there cannot be material or energy flow unless the corresponding partnership has been activated, right? This is important. So the optimization problem answers a very specific question for each scenario: which exchange should be activated and how much resource should flow between firms, right? So the firms, after solving the 100 scenarios, the application presents the result in 2 ways. First, it provides the aggregate analysis across all scenarios, which includes the partnership frequency, and we can see here that what is the frequency of the partnership, the frequency of the activation for across all the 100 scenarios. For example, just to see in this plot, we can see the Fagor can provide waste heat to replace the electricity of Mondagron University in 91 of the cases. So in 91 of the scenarios, the optimization problem found optimal to use this particular partnership synergy. So this is, on the other hand, the average flow is the average of waste that they find optimal, and then the maximum flow, depending, is 71 megawatts of waste heat, and so on. So we got complementary information that can be quite relevant. On the other hand, for the plastic and polymer relationship, we found 2 main partnerships: Fagor to provide plastic scrap to Mondagron University, and the 4th firm to provide the same synergy to the Mondagron University with 77%. So this is quite robust and reliable. So this what is telling us the application here is that identify those partnerships that are more robust, those that they are over 70% of the scenario activity. So, because we are running out of time, so we got also some statistical analysis.
Sorry, Oscar, to interrupt yourself. There are some questions of the audience, so I will suggest you to finalize in 1 minute to allow me to ask you the question.
Okay, right. So what we have seen so far, they are the optimal solutions, and so the other 3 tabs are mainly to present the result in a more interactive way and in more illustrative way. And so we have on this tab the total cost distribution, the resource utilization, and therefore we got the same information presented in different ways. So we also have the network topology. We represent what partnership are the more strong and the work conditions. We can check every single scenario to see which partnership is more relevant. And then we also have the complete data that will analyze scenario by scenario and to see which specific conditions are the ones more positive to implement a particular partnership. So this, then finally, just we got the network visualization, and well, this is another way to probably when the application is fully developed, we need to provide some geographical illustration visualization of the result, and this is especially good for reports and to communicate to external partners and so on. So that I could say that there are also we also use some artificial intelligence, but rule-based artificial intelligence to provide recommendations to see what partners are the more robust and which one are probably they need further study or further exploration before they should be implemented. So this is in general the application. So because as you said, we are running out of time, and I would like to go into more the details. But again, in the paper are the formulation, and always there are opportunities to go to the user guide to go into the documentation and so on. So thank you for your attention. So if you got any question.
Yes, there are some questions from the audience. I'm going to start with one of them. It's from Aida. Tim asked to you, what is the meaning of electricity needs? Is the electricity energy consumption of the company?
Yeah, exactly. So when we say that we identify the type of waste and the primary inputs. The primary inputs are the ones the companies need to use to carry out their business activities. It could be, I don't know, if they are building cars, so they need how much consumption of energy, specific electricity is the primary input. So this is the kind of data we need for the method, the input and output method, and we need mainly the total production of the company. What is the coefficient, how much waste is produced per ton of production, and how much primary input is needed for each ton of production. So in this case, electricity, we need 13 megawatts per hour of electricity to build 1 ton or one product, but that's what we consider in this platform.
Okay, thank you. There is another question from Ana Ramos. Could you please clarify how frequently are the variables, for instance, the economic one, updated so that the optimization is solved with the most accurate set of results?
So Say again?
Yeah,
Sorry.
she would like to know the frequently that the variable that you have, like the economic one, are updated to ensure that the optimization is always accurate for the result.
Uh, uh, what we do is I don't know if I got the question right. I mean, it's the optimization problem is run for each scenario, and the critical variables we change are the quantity of supply of waste and the demand for primary input. And for this, for each scenario, which is represented by these two parameters, we run the optimization problem. And then the cost, obviously, depending on the cost, that determines, you can do some sensitivity analysis to see how each of the costs and the objective function provide change the result. So that could that could enhance the robustness of the model to see how changing the cost would. But I don't know. That's what she's asking for. Yeah.
She also asked you another thing, which database are behind the estimated data in case no real data is providing or none.
So the data is well, is that's one of the things we are working on it, and it will depend on the sector. That's one of the main steps we are going to do, and obviously there are some databases there, and we can also there are some input and output tables. Even though these input and output tables are in monetary terms, there are ways to transform these tables into physical tables, and then the other piece of data we need is, as we said, is the coefficient of how much waste is generated and how much primary input is needed. So these are all coming. They are provided in reports, environmental report, and specific for each sector. But mainly we extract all the information from input and output tables and report.
Okay, thank you. Another question. What about the competitive use of the residues? In case this or a part of them are already being used for other revalorization scheme.
Okay. Yeah, that's a good. We are not dealing with the competition here in this platform, but in the paper we are. In the paper, we use a grading algorithm, and they allows the grading algorithm to give priority to those partnerships that are more economically viable. So if they are competition, there are two providers, two ways can replace one primary input or other or vice versa. But that there is an algorithm that allows to decide which pathway is the most economically viable. But that's one of the things that we do in the paper, but we omit here. But that's an interesting point. Yeah, that's amazing.
Oscar, another question is if there are any guideline available for the users.
Baseline.
User guides.
Yeah,
Guideline, yeah.
Yeah. We got here, but I have to admit this is a proof of concept. It had never, this is a version that we use to communicate and to express, basically to share what we are going to do in the future, where are we heading. We got a more advanced version, and we obviously the user guide here in this tab can give you an overview of what we are doing, what are the main features of the application. But obviously, this is only a proof of concept that this is starting point, and that's why we are developing this further. So, yeah, all information is there, but it is probably we've got a new version now, and in a few months' time, we will have different versions that will refine and provide a more comprehensive way to establish synergies between different firms.
Thank you so much for the clarification. Another question is, has the tool already been used as a decision support element in a real industrial symbiosis synergy?
No. This is we are refining the tool to capture one. This work we carry out this work with Sena Dash from Mondagron University. Hopefully, it's in the audience as well. And we are planning to develop this, and we are going to focus on one particular material, steel industry. So once we have, instead to have three primary inputs and three type of waste, we are going to focus on metal scrap and other different waste. And we are going to see how we can apply that to a more to one cluster in the north of Spain or in any other industrial estate across Europe. But the first thing we are going to do is to focus on one sector. It's going to be steel, and to define all the possible partnerships that can be realized. And then from there, we are going to apply to a proper industrial estate. So this is only a proof of concept, cannot be applied to any. But we'll go a more advanced version now.
We will wait for this real application and your inputs on that. Thank you. And last question, because we are around out of time. They would like to know if there is any kind of filter to avoid using, let's say, no authorized type of residues like the medical waste in your platform. Yeah.
So you mean that the optimization problem only doesn't consider any specific type of waste or something like that? So
yeah, they are like meaning if there is a filter or a kind of setting in the platform to avoid, for example, medical waste or something like that or toxic waste.
No, but that could be one of the features we could include in the actual app. Yeah, that could be interesting to say. Well, as I said before, we are gonna only focus on one sector, and then probably there will be steel manufacturing, and probably we don't expect to come across this kind of waste, but probably in the future, yeah, that can be extended. Yeah, that's an interesting point. Yeah.
Okay. So, Oscar, thank you so much for answer all the question and also for your kind introduction to SYMBIOPTIMIZE. I think that the result when that will be like a real implementation will be really nice. But even though I think that for our audience will be interesting to go deeply on the platform and contact you for more question and more clarification. So once again, thank you so much for being here, for your presentation, and also for all the audience to ask questions and to also to be present today. So the recording will be available in our YouTube channel in the coming days. Thank you so much and have a nice weekend.
Okay, thank you very much.
Bye.
Thank you. See you. Bye.